Welcome to the QuickStart tutorial for AFT Aero 4.0. This tutorial will teach you the fundamentals of using and understanding AFT Aero 4.0. Prerequisites include passing an undergraduate engineering course in the analysis of compressible fluid mechanics, as well as familiarity with standard industry practice in compressible pipe flow analysis. AFT Aero is a general-purpose tool for modeling pipe network hydraulics with compressible fluids. Aero calculates pressure drop, flow distribution, and an energy balance. Aero can model the equation of state using ideal gas or a variety of real gas models. AFT Aero can model all gas systems where the fluid is compressible and single phase. Aero models open and closed systems that are pressure driven or driven by a compressor or fan. Aero offers customizable component and property databases. The engineering assumptions and limitations required to use AFT Aero include steady-state operation and a fluid that is compressible, single-phase, and Aero can't directly model change in fluid properties due to chemical reactions. AFT Aero is broken into 5 primary windows. The workspace and the model data windows are primarily for building and defining your system, while the output, the graph results, and the visual report are primarily for reviewing the results. Let's explore the workspace in more detail. To build a model, you will be using the toolbox on the left-hand side of the workspace window. This is broken into 4 drawing tools at the top of the toolbox and 20 junctions at the bottom of the toolbox. To draw a pipe on the workspace, simply click on the pipe drawing tool and then draw a line where you would like your pipe to be located. To place a junction on the workspace, simply click on the junction and then drag and drop it onto the workspace. To move a pipe or junction, simply drag and drop it where you would like to move it to. To move one end of a pipe, you can either drag and drop the handle on the end of the pipe, or you can move the connected junction. To enter input data, simply double-click on the pipe or junction and a specification window will open. The specification window is the platform for entering data to define the pipes and junctions throughout your model. To help you identify the minimum required input data, we have highlighted those cells in blue. We will be disabling the blue highlight feature for this QuickStart tutorial in order to make the data entry easier to see. To toggle the highlight feature on or off, you can double-click in the background of any specification window. There's a checklist in the bottom left of the screen which indicates what needs to be completed prior to running your model. The red light on the left will turn green after you are ready to run your model. The solution control, the output control, and the cost settings are all defined by default. We will discuss these checklist items in greater detail in a future tutorial. The System Properties window is where you define your fluid data, your viscosity data, and your system data. In order to fulfill the Define Pipes and Junctions checklist item, you must first construct your model in the workspace and fill in all the required data for each pipe and junction. Now let's dig a little deeper into the toolbox. The pipe drawing tool allows you to draw pipes on the workspace. Keep in mind that every pipe must be connected to a junction on either end. The minimum required input data for a pipe includes the hydraulic diameter, the pipe length, and a friction model. To help you define the pipes in your model, we have provided a pipe material database which allows you to select standard pipe materials, sizes, and schedules. As thermodynamics are intrinsically coupled with gas dynamics, AFT Aero will always calculate heat transfer throughout your system. You can choose to model heat transfer in each pipe throughout your model using one of 4 different heat transfer models. By default, we will model all of the pipes as adiabatic. The lower portion of the toolbox contains 20 junctions to help you model your system. The tank junction acts as a pressure-type system boundary, sourcing or sinking fluid to or from your system. The branch junction is used as a generic connection between pipes. You can connect up to 25 pipes to this junction. By default, this junction balances mass flow, so all flow into this junction is equal to all flow out of this junction. The valve junction can be modeled a number of different ways. The subsonic losses can be defined with a user-specified constant CV, an open percentage, a constant or variable K-factor, or a resistance curve. Alternatively, you can select a loss model from our handbook database containing various options from Crane, Idlecheck, and Miller. The compressor or fan junction allows you to define how the fluid is propelled through your system. You can define your compressor or fan as a volume or mass fixed flow rate, a fixed pressure or head rise, or using a curve. You can define your curve using either a volume or a mass flow rate versus either a head or a pressure rise. Optionally, you can also include efficiency or power curve data. Now let's build a simple compressed air system as shown below. The purpose of this model will be to determine the delivery conditions at 4 different tools. Air will be taken from outside to supply 4 machine tools, so we will define our system fluid to be air. Notice that our system properties are now defined. Now let's build the model using the toolbox on the left. Notice that as you hover over an icon in the toolbox, there are shortcuts that appear in the bottom of the left pane. If you hold down the Control key on the keyboard, you will be able to draw multiple pipes consecutively without having to re-click the pipe drawing tool every time. The machine tools are sensitive to temperature, but the manufacturer says they can compensate for this if they know the extremes of delivery temperature the tools will see. We will evaluate the operating conditions that will result in the hottest delivery conditions first. In the interest of time, I will only show how to define one pipe in this example. Pipe 2 is 25 feet of uninsulated 2-inch Schedule 40 steel pipe. The system conditions that will result in the hottest delivery fluid temperature will happen when the building ambient temperature is 75 degrees Fahrenheit with an external convection coefficient of 1 BTUs per hour foot squared Rankine. If you are following along, please pause the video and enter data for all the pipes in your model as shown below, using a convective heat transfer model with a 75 degree Fahrenheit ambient temperature and an external convection coefficient of 1 BTUs per hour foot squared Rankine. We will assume that the pipe at the compressor inlet, P1, is heavily insulated and therefore adiabatic. For the hottest delivery conditions, we will model the outside air at 110 degrees Fahrenheit. All elevations throughout the system will be set to 0 feet. The compressor has the following data, and for the hottest delivery conditions will be assumed to operate at 80% efficiency. In order to account for the compressor heating the air due to the defined inefficiency, we will select Determine from Efficiency Data under the Compression Process Thermodynamics option. The branches can be modeled as lossless at an elevation of 0 feet. The data has already been entered in this model. You can double-check input data by right-clicking on any pipe or junction. The nozzles at the tools, which are being modeled as valves, have a pressure drop of 8 psi-d at 0.2 of a pound per second, discharging to atmospheric pressure. As we only know a single data point, we need to make some assumptions. Because pressure drop increases non-linearly with flow, it is usually fairly accurate to use a resistance curve plotted through the 0 point, the known data point, and an extrapolated quadratic data point. If you enter the known data point and then click the button Fill as Quadratic, Arrow will generate the 0 data point and the extrapolated quadratic data point for you. We will be modeling the nozzles as exit valves, discharging into external conditions. You can reduce the time required for data entry by using the Global Edit feature or the Duplicate feature, both of which can be accessed through the Edit drop-down menu. You can also speed the process by using the Copy Data option within a specification window. Notice that now our model is fully defined and we are ready to run it and review the results. Before doing this, let's clean up the visual layout of the model. It's easy to move text labels and rotate junctions on the workspace in order to make them look more aesthetically pleasing. Now that you're familiar with the workspace window, let's review the second input window, the model data window. The model data window is a useful tool to help you review the input in a text-based layout. It's easy to give your model a sanity check by scanning down each column and looking for wrong units or double-checking orders of magnitude. The input here is not interactive, but you can double-click on a row of the table corresponding to any pipe or junction and bring up its interactive specification window in order to modify any pipe or component input. Before you can run your model, the final step is to save your model. This model has already been saved as QuickStart tutorial.aro. Now let's run the model and review the results. The output window looks similar to the model data window, except that now we are looking at the results of the analysis rather than the user input. For the input conditions that result in the hottest delivery conditions, we can see that the maximum delivery temperature is 202.28 degrees Fahrenheit. The input conditions that result in the coldest delivery conditions are shown below. There is an outdoor ambient temperature of 0 degrees Fahrenheit, an indoor ambient temperature of 70 degrees Fahrenheit, an external convection coefficient of 10 BTUs per hour foot squared Rankine, and the compressor efficiency is 90%. The Global Pipe Edit feature will make short work of changing the heat transfer configuration to reflect a lower indoor ambient temperature and a higher convection coefficient. Remember that P1 is heavily insulated, so we are modeling it as adiabatic. For the input conditions that result in the coldest delivery conditions, we can see that the minimum delivery temperature is 65.63 degrees Fahrenheit. Based on the two extremes in operating conditions, we can confidently tell the machine tool manufacturer that the tools will always have their air supplied between 65.63 and 202.28 degrees Fahrenheit. This concludes Part 1 of the AFT Aero 4.0 Quick Start tutorial.